Hello and welcome to this film, which is all about another spectrum. This time it's not about a mass spectrum, and hopefully you've watched the last couple of films about mass spectrometry. This time we're talking about the electromagnetic spectrum. Now, the electromagnetic spectrum is basically a range of different types of light. So hopefully by the end of this film you'll be able to describe light, or electromagnetic radiation, to give it its proper name. You'll be able to describe it in terms of its speed, its frequency, its wavelength and its energy. Okay, so let's have a look at one way of representing the electromagnetic spectrum. Now here we've got all the different regions of the electromagnetic spectrum, so the whole range of different wavelengths of light arranged in order of decreasing wavelength. So these numbers here at the top describe the length of the wave. So light or electromagnetic radiation travels as a wave, and the distance between one hump and the next, or between here and here, okay, that's described as one wavelength. Okay, and if we measure this in meters, then we can see all the different wavelengths of light, ranging from radio waves all the way through to gamma rays at the very short end of the scale. And you will see also that in the middle of this range are the different wavelengths that we can actually see. Now, if we talk about electromagnetic radiation as light, the danger is that we focus on the things that we can see, so they're the different colours of the rainbow. So Richard of York gave battle in vain, or simply Roy Gabiv: red, orange, yellow, green, blue, indigo, violet. Okay, so these are the different colours of the rainbow that we can see, but that doesn't mean that this is the only light there is. Okay, so at a wavelength longer than that which we can see at the red end of the rainbow, there's infrared radiation, and there's microwaves and there's radio waves. At a wavelength shorter than that which we can see, so at the violet end, or just beyond the violet of what we can see, is ultraviolet radiation. Okay, so there's this great big long spectrum or range of different wavelengths of light or electromagnetic radiation that exist. We can see a very small range of them, but that's not because that's all there is, but because our eyes can simply only detect quite a small range of wavelengths. Now what we're going to do is have a look at how the wavelength of the light is related to the frequency, and also how the energy of the light is related to the frequency and therefore to the wavelength. Okay, so here we've got this equation which you'll probably use quite a lot in physics. You don't really have to do any calculations with it in chemistry. I'm just showing you it here so that we can make a kind of qualitative, so no numbers statement about the relationship between energy and wavelength and frequency. This equation says, no matter which way we read it, E, the energy of the light, is equal to Planck's constant h times the frequency of the light, which when I learned it was given the symbol nu. I've seen it on a lot of physics papers used as where it's simply given the symbol f for frequency, and obviously that one seems to make a lot more sense, but there you go. So if we take the frequency of the light and multiply it by a constant called Planck's constant, we'll find the energy of that light. Also, we can see that the speed of light, which is another constant, is equal to lambda, the wavelength of the light, times the frequency. And if we rearrange this, we'll see that the wavelength of the light is equal to c over the frequency, or c over nu, or c over f. Now what does that mean for the relationship between the wavelength and the frequency? Well, hopefully you can see that that means that lambda is proportional to 1 over the frequency, or the wavelength of the light is proportional to 1 over the frequency. Okay, this means that the longer the wavelength becomes, the lower the frequency is, and the shorter the wavelength becomes, the higher the frequency is. Now you might even be able to just decide this from the fact that if the wave oscillates very, very rapidly, then it must be doing so in a very short distance. It must be making each oscillation in a very short distance. So here we've got very high frequencies. Okay, you might remember that on the previous slide we looked at it with the very short wavelengths on the right. So we haven't flipped the spectrum round here, we're just describing it in terms of the frequency of the light now instead of its wavelength. So here we've got big numbers on the right, small numbers on the left. And once again you can see here the visible region of light. So on this end of the visible spectrum, at the violet end, ultraviolet comes next. It's got high frequencies. Remember, that means it's got low wavelengths or short wavelengths. What does it also mean? It means it's got high energy. Okay, so at this end of the scale we've got high frequency, short wavelength and high energy. At this end of the scale, so the red end, we've got low frequencies, long wavelengths and low energies. Okay, now, as I say, it's not important to do calculations with these formulas in chemistry, but what it is important to realize is how the visible range of frequencies or wavelengths is related to their color and to their energy and to their frequency and their wavelength. Okay, so we should know that when we arrange the colors of the rainbow from red to violet, we should be able to figure out which ones have the longest wavelengths, which ones have the highest frequencies and the highest energies, and so on and so forth, okay, without having to do calculations with them. Okay, so there we go. Hopefully you now understand what it is we mean by the electromagnetic spectrum. It's going to make it an awful lot easier for you to understand what's going on in absorption and emission spectroscopy if you do understand this stuff. Okay, so if you can make qualitative statements about how these four things, the speed, the frequency, the wavelength and the energy, are related. Okay, so no calculations, but you do need to be able to relate these things in your mind, otherwise the next couple of films about absorption spectroscopy are going to be a little bit mysterious. Okay, so as I say, hopefully it makes sense. If you've got any questions or comments, then please feel free to come and see me or to post a comment on YouTube.